presentation or okay, yeah, no, I can share it now. Can you see it?
Yes, doctor.
Yes. Okay, so we're talking about the disinfectants, or just to recap, we are going to discuss about 3 types of disinfectants. With ozone, with chlorine, and with UV. The most important concept about the disinfection process is the CT factor or parameter, that is the concentration times the contact time. When we are talking about chlorine, that happens usually in this type of units, and once again has to be after the drinking water processors or after the wastewater treatment processes. After these processes is where we do the disinfection step. If we do it with chlorine, the CT values suggested for the most common waterborne pathogens are these ones. So in the case of Escherichia coli, we can use a CT factor of between 0.034 to 0.05 to remove, for example, viruses like poliovirus of 1.1 to 2.5, Giardia muris 630, and Cryptosporidium more than 7,200. And these are values suggested to achieve a removal of 99% of inactivation of the organisms. Now, chlorine is quite strong, but their use is not that suggested anymore because of the formation of some products that can be carcinogenic. So another disinfectant that is suggested is ozone. Ozone is more powerful than chlorine, but it tends to be a bit more expensive. Yet, despite that it is more expensive, some of the advantages of ozone is that the effectiveness of ozone is not affected by the pH or by the presence of ammonia. So the optimal values for disinfection with ozone are not influenced by the pH. So regardless of the pH that we apply, it can be quite effective. And because ammonia is not present in very high quantities, therefore, the disinfection can be quite high. Also, is not directly linked to the presence of some transformation by products, so doesn't leave residues, or some will volatilize. When we use chlorine, there are suggestions that say that we need to use or implement some dechlorination steps to avoid that chlorine is present in the water. Well, depending on where you are doing it, when you are dosing it. But in the case of ozone, there is no need to have a step to remove any residual ozone. It can be, or because it is much more powerful, it needs, for most of the microorganisms, the most resistant microorganisms, it can have a CT factor of 1 to 3. If we look at the values that are required for ozone, for example, in the case of Cryptosporidium, we need to have a CT value of more than 7,200 when we are adding chlorine. Whereas when we're using ozone, the CT value can be only of between 1 to 2, 3. So that helps in having a much more efficient disinfection process. So these are some of the CT values suggested for disinfection of these indicator organisms. If instead of chlorine, we use ozone, the CT value for E. coli is of 0.006 to 0.02. For the removal of viruses like polio, rota, adenoviruses, we need values of 0.72, even lower for rotaviruses, 0.064, or up to 2.6 if we are targeting the virus Coxsackie B5. And for protozoa like Giardia lamblia or Cryptosporidium, that is one of the most difficult ones to remove, we need CT values of 0.53 or 3.5. So this is way much more effective because it's much more stronger than chlorine. Now, if instead of chlorine or instead of ozone or chlorine, we use UV disinfection, UV is gonna be the exposure of the water contaminated with these microorganisms that will be inactivated because of the UV effects. And this UV is not added into the water because, of course, it's not a solution, but it is a light, UV lamps. Nowadays, there are some UV lamps that are made of, for example, LEDs that are much more economic. And these LED lights are installed in the disinfection tanks in such a way that there is exposure, there is a light penetration of the UV through the water. And due to these characteristics, the water depth has to be relatively shallow. So there is a good penetration of the UV light, and more important, UV light has to be applied after certain filtration process. In order to make it a bit more economic, filtration, like sand filtration, can be a bit more economic than applying some membranes, mostly to clean and get rid of some suspended material that can or may interfere with transference of the UV light through the water, achieving a higher disinfection level. How does it work? Well, when we have the UV light is located in this range. So here we can see the UV spectrum. So this is the visible light, the light that we can see with the bare eye, different tonalities. Here we have a wavelength of between 400 and 780. Then we have the infrared, and below the UV or the visible light, we have the UV light, the ultraviolet. This ultraviolet goes from 100 to 400 nanometers with different levels of UV, like UVA or UVV. The most strongest disinfectant level is provided by UVB, and this is a bit lower. Sorry, it's for UVC. It's at 254 nanometers, and this is the UV light that has the strongest inactivation, the UVC. Solar light has a combination of different levels. Solar light, sunlight can have mostly UVA or UVB, but the most effective is UVC with this level. What does it cause? Well, it causes a damage of the enzymes, a damage of the DNA strands, the DNA chains of the organisms, breaking the enzymes, damaging the way how this is structured, and because of that, reducing or limiting their levels that they have to proliferate. This is how the UV light works. Now, because UV is much more stronger, and because it is based on the incidence or in the transmission, the exposure to this light, well, here it is measured in terms of the watts that are needed per square meter of the lamp per second. And these are the values that are required to achieve a 90% reduction of these different types of organisms. And we can see how, for example, for Helicobacter, Campylobacter jejuni, that these there are some of the less resistant. We need an ultraviolet dose of only a bit more than 1,000. And the strongest ones are, for example, for adenovirus, that we need 56,000, Cryptosporidium, 3,000, etc. So these are some of the values that are having measured to lead to a 90% reduction or inactivation of these microorganisms. So these are three different ways or manners to disinfect. They are also the same, let's say, advanced processes that can be used for the removal of contaminant or emergence contaminants of emerging concern. Do you have questions?
No, no, doctor.
No questions. Well,
It's all okay.
so these are the levels. So when we are applying, for example, the UV light to achieve 99% inactivation. So this is just a summary of what is the intensity that we require. The simplest ones are, for example, the microsporidia or some small certain viruses, giardia. So for those ones, we need an IT of around 10 more or less, intensity times time. If we have some other viruses that are stronger, or adenoviruses that are the strongest ones, then we need an IT of more than 100. So this more or less exemplifies this IT is the intensity of the light times time. So similar to the CT concept, but in this case applied to UV light that we need to be achieved. And these are different levels of survival measured in different types of waters, targeting adenoviruses, Coxsackie viruses, polioviruses, for example. And we can see that the most difficult one to remove is adenovirus. Adenovirus, these are the log of survival. So how they get disinfected, and logs. One log means that the system is disinfected by so one log is a disinfection of 10 times. So this is 10 times, 100 times, 1,000 times, 1 million times, etc. Sorry, is 10, 100,000, 10,000, etc. times the number of elements disinfected. With this, we finish, and we can continue with the design exercise. So these are some values. I gave some information about the importance of these pathogens, or the relevance of the removal of these pathogens. And with the values that we have discussed, now we can do some calculations to estimate what are the conditions that we need to remove or lead to the inactivation of these organisms from the water. Do you have questions?
It's all okay, doctor.
Okay, so then we can I will change my screen. I sent to you a bit before the exercises. So I will open those exercises. I will see where I have them. Here they are. So there are it is one exercise, but to assess different conditions. So I will share again my screen, but now with the exercises, you have the handouts. Can you see the screen?
Yes, yes.
Okay, so now based on what we have seen, now in the next period, we are going to do some estimations for the removal of these of some pathogens. So what can we use, or what do we do to estimate, or to get some let's say preliminary estimations of the removal of these pathogens? So it is the same system. The exercise is or considers the disinfection of certain water that is going to be supplied to a small town using chlorine disinfection, using ozone disinfection, and UV disinfection. So the exercise says that, well, there is a small town that has 2,000 inhabitants, and this water, well, this generates certain wastewater. It has generation of wastewater of around 360,000 cubic meters per day, but has a maximum peak wastewater flow rate peak of 9,000 cubic meters per day. So this is the average 360,000, but because 3,600, but because of the rainfall, the water can have up to 9,000 cubic meters generated every day. Now the question is, okay, but the plant has has already a disinfection unit. Has a disinfection unit that has a volume of 75 cubic meters. And based on different studies, the CT values of different pathogens have been estimated. So the disinfection unit has 75 cubic meters. The disinfection units, and this is what we have seen in our lecture. So these are different pathogen indicators. We have Escherichia coli, we have a virus of polio, also some other types of viruses, Giardia lamblia, Giardia lamblia cyst, and Cryptosporidium oocysts. And for these conditions, these are the CT values that grow from 0.04 to 7,200 for the case of the cryptos oocysts. The question is, if the plant is already built, first, the question is, what is the average contact time in the disinfection unit? Or what is the contact time in the disinfection unit in minutes? And then the second question is that, assuming an average free chlorine concentration of 1 milligram per liter that is dosed in the disinfection tank, what is the required contact time that we need to achieve 90% inactivation, and if, based on those conditions, if all the pathogens are going to be inactivated? How do we answer this question? How do we start? So it is a plant, has a flow rate of 3,600 cubic meters per day, maximum 9,000. The plant has a disinfection unit of 75 cubic meters. We are asked to assess whether these organisms are going to be inactivated if there is a free chlorine concentration of 1 milligram per liter. So what do we do? How do we answer this question? Any suggestion? What do you do?
I think calculate the CT.
Calculate the CT. The CT is okay. What CT? We have the CT. Just you can see my screen, right?
Yes, yes, doctor.
Yes. So these are the CTs of these are the CTs needed for per organism. So what CT are we going to calculate then? So your answer is correct, but what CT do we need to calculate?
I think according to types of organism, like
well, these are
E. coli.
These are per organism.
E. coli and viruses like polio 2 and Cryptosporidium. I think according to types of organism.
Okay, but the first so you are right. So we need to calculate the CT. So CT constant, but which CT constant? You are is more or less okay your answer, but which CT constant? because we already have the cities of the organisms. So what
Oh,
CT do
yeah.
we need now? What is C and what is T?
I think C is the concentration and the T is the time.
Okay, which concentration?
The concentration of disinfection material that does.
Exactly.
Hmm.
Yeah, exactly. So this is the these are the concentrations that we need to get the microorganisms inactivated. Now, this is what we need. This is what is going to kill them. This here is the concentration, the CT, that the disinfection tank can achieve. So this will be the CT, etc., of the disinfection tank. The disinfection unit has its own, can create certain CT. The question is that CT sufficient to inactivate the organisms? So this will be the CT of the disinfection unit. So the disinfection unit, the tank, has a volume of 75 cubic meters, and during the peaks or during the day, the water volume that passes through the disinfection unit can go from 3,600 cubic meters per day to 9,000 cubic meters per day. So we have, I will duplicate this slide. So I can move this one. So we have a disinfection unit. The disinfection unit is usually an elongated tank. It is a tank that is built with a length to width ratio of around 1 to 20. So these are very, these tend to be, if I am talking about the geometry, the length to width ratio of these tanks is of around 20, meaning that the length is approximately sometimes 20 times the width. So they are very elongated tanks, so that tend to be built in in rectangular, in a plug flow configuration. So the water gets into these, then it goes to the next tank. So it's flowing like this. It flows from one tank to another, and then it goes to the next stage, etc. And the water is flowing through this disinfection unit. Oh, 1 second, sorry. Till the water passes through this disinfection tank and then flows out on the other side. So because the width, this is the width is a dimension in this, and the length is a total length. So it will be like the sum of this length plus this length plus this length. That will be the volume of the disinfection unit. Now, the volume, so by water by hydraulics, the time that the water spends in this unit, the time is function of the volume of this contact time divided by the flow rate that passes through. So for this case, and this will be equal to the contact time. This will be the contact time. Now, the volume is fixed. The volume of this system is already given, is built. So the plant has a disinfection unit of 75 cubic meters. So we have already the volume of this disinfection unit. Volume is equal to 75 cubic meters. But the flow varies, and that's normal. In every plant, the flow rate changes because in the morning people use more water, maybe because they have breakfast, they have shower, etc. Maybe after a few hours they go to work, so they produce less water. They come back for lunch, they produce more water at midday. Then maybe it starts to rain. There is more water reaching the plant. Then in the night there is not too much water, or there is less water consumed, or maybe after dinner. So water is always fluctuating. So from that perspective, what flow rate do I take into account?
I think
conservative.
I think the big one.
The big one, exactly. Why the big one?
Because this is the worst case.
Exactly. Very good answer. Because if we have a lot of water, the water will pass faster because it's more water, smaller volume. So the time that the water will spend there is going to be minimum. So that is the worst case scenario. So the flow rate is 9,000 cubic meters per day. So with these values, the disinfection units are given usually in minutes. So the best is that we can estimate the contact time also in minutes. So for that purpose, I can convert these to cubic meters per minute, and that will be equivalent to divide 9,000 by the 24 hours of the day and the 60 minutes that every hour has. And that will tell us that the flow rate is gonna be 9,000.
6.25.
Thank you very much. 6.25 cubic meters per minute. Thank you. That means that if I replace those values here, the contact time for this worst case scenario, contact time T, I have to use lowercase t because otherwise capital T is temperature, will be the 75 cubic meters divided by the 6.25 cubic meters per minute. And this tells me that the contact time is
12
minutes. Okay. For these conditions, the contact time is 12 minutes. Now, okay, now I have the first value. I have to find the CT of the disinfection unit. I have the first one, that is T. What concentration? Let's review the information. This is plant and it's working. We are dosing 1 milligram per liter. The average concentration is 1 milligram per liter dosed. So that concentration is 1. What means that the CT or the disinfection unit will be concentration 1 milligram per liter. Move this to the right. Will be 1 milligram per liter of chlorine times 12 minutes. So my CT value is 12. 12 milligrams of chlorine per liter, and this per minute. What does it imply? This is the CT of the disinfection unit. What is this value? And how then can I use it?
The CT is the disinfection material and the time the time needed for a 99% in activation of microorganisms.
Okay, and then and what does it mean for this case? The CT that I can have in my system is of 12, and the CT that I need, for example, for E. coli is 0.04, and I can create 12. So will this E. coli be removed or not?
Yes, it will be removed.
It's removed because for E. coli I need 0.04 and I have 12. Okay, so this will be removed. Perfect. So I can say, okay, this is okay. So I will turn it green. So this is removed. Perfect. What about the other coli? Also, what about the poliovirus?
I think the other values is can't be removed by this disinfection.
Exactly. So when I reach this level, so based on the CT, this coli and poly1 virus, they can be removed because the system can reach 12 and they need 1.7, 0.6, 0.0. So this will be disinfected. But what happens with this HAV virus? It needs 12.3 and I have 12. It cannot. And the same happens for the rest of them. So this one cannot. This one cannot. So none of the rest will be removed. I need 12, but the system can only reach. Sorry, I need different ones, but the system can only reach 12. So this cannot be removed. Perfect. Okay, so assuming that there is an average free current concentration of 1 milligram, what is the required contact time? The contact time, well, we have 12 minutes, it is fixed. And are all the pathogens inactivated? No, we can't. Okay, so what is the next question? The next question is, if the free chlorine concentration is increased to 4 milligrams per liter, can we inactivate all the pathogens? And if we cannot, then what is the required contact time to achieve that inactivation? Okay, if the free chlorine is increased, so that means that if it is increased, so I will not use 1 milligram per liter anymore, but now I'm gonna use 4. So if I use 4, the CT of the disinfection unit will now increase from 1 to 4, and then I will have here 4 times 12 is 48 milligrams of chlorine per liter. Now, if I have 48 and if I come back, now the disinfection is 48. So for the second case, if I don't use 1 anymore, but 4, this will increase to 48. This will also be 48. All of them are going to be 48. So now I will reach an inactivation of most of them, or of more of them, but up to eco 1. So this will be now removed. But I cannot remove above Giardia lamblia. So Giardia requires 70 and I have only 48 if the concentration is increased to 4. So what else can I do? So if I check the values, I see that is 48. That is not sufficient to inactivate Giardia lamblia and is very far from inactivating Cryptosporidium. So what do I need to inactivate, for example, Cryptosporidium? Because that is a question. So if not, if they cannot be removed, what is the contact time that I need to achieve 90% inactivation of pathogens? What do I do?
I think we need 150 minutes. We divide.
So yeah, you are right. So if for I can take the most difficult